For this part of the video, we go through iteration. In the previous part, we did recursion, which is a form of repetition, a very important part of a program, besides the sequence and conditioner. And here we see directly iterations. The repetition is with statements like while and for within the program, rather than calling the function in a recursive manner. Since recursion and iterations are serving the same purpose in some sense, let's recap those examples that we saw for recursion and try to see how to solve them in an iterative manner. First example, factorial. Factorial is equal to n times n minus 1 times n minus 2 until 1. So recursively is written as n factorial equal to the base case of 1, or is equal to n times the smaller problem of n minus 1 factorial. Now, how do we think iteratively? Well, looking at this definition, you need to take the input n and multiply by 1 less than it and multiply with 2 less than it until it's 1. This is perfect for the construct of a while loop. To repeat, we say that we start with n, then we need to do multiply by n minus 1, then multiply by n minus 2 until 2 or until 1. This is perfect for while statement, and it does the work. The work are here, the two statements here, as long as n is larger than 1. Initially, the input n comes in, the answer is set to be 1, and then the answer got accumulated each time it multiplied with n. So the first time the n comes in, it's multiplied with 1 to get answer n. And then n is minus 1 to go to the next number, and then this is repeated until the very last when n is exactly equal to 2, and this will finish, and then n become 1, and 1 is no longer larger than 1, and it stops, and you return the answer. So this is factorial. Let's look at a specific example for this program with n equal to 5 to trace the code. Tracing of code is a common task that you as a beginner in programming has to do to better understand the behavior of a loop. Here the loop means the while loop. Bugs in programs are usually because of looping and not on sequence or conditional statements. We often miss out one or do extra one loop in a buggy program. For tracing, we use a small example like n equal to 5, and we have a table to keep track of important variables. In this program, the answer and n are the important variables to keep track of. As a start, the input n equal to 5, we have n equal to 5. Next, the answer is equal to 1, so answer is 1, while n equal to 5. While n greater than 1, yes, 5 is larger than 1, so it goes into the body. And answer equal to 1 times 5 to give you answer 5, so you have 5. Then n equal to n minus 1, now n from 5 become 4. Then you go back to the loop, and n greater than 1, yes, 4 is larger than 1. So you continue. Answer is equal to 5 times 4 to give you 20. So you have 20. Then n is equal to n minus 1. So from 4, n become 3. So 3. Go back. And 3 is larger than 1. So you continue. Answer is now 20 times 3. Give you 60. And you continue. N equal to 2. Go back. 2 is larger than 1. So you continue. You have 2 times 60 to give you 120, and now becomes 1. And then go back to check the condition. In this case, 1 is not larger than 1, so this failed, and this loop is exited. You reach this statement to return answer, which is the answer is 120 as what you needed. So this code is okay, and with this tracing. So once again, in tracing, you have a table like this to keep track of important variables. In this case, we have answer and n, the two important variables to keep track of. So for n factorial, we thought of it as n factorial equal to n times n minus 1 and so on. Actually, we could have thought of it as 1 times 2 times 3 until n also. So this gives us another iterative solutions. We can start with 1, multiply by 2, multiply by 3, and so on until you multiply by n. So here is the code. In this code, it is the same as the while here, except that now we write some shorthand for you to get used to. Answer star equal to m is the same as answer equal to answer times m. So the answer is shorthanded with a star equal. Same for this, m plus equal to 1 is the same as m equal to m plus 1. Okay, so this code is close to this code, except that now this is from 1 all the way until n. And we don't have to do 1 actually, we just have to do from 2 onwards. If n is equal to 1, the answer is equal to 1. You just don't go into this loop. Okay, so this is the while loop. While m as a counter that it's keeping track of, as long as it's smaller than n, you will continue accumulating the answer, and m is incremented by 1 until the end. Let's do a tracing again. Our tracing is on the example of n equal to 5 as before, and there are two important variables for us to keep track of. They are m and answer. So to start, we have answer equal to 1 as this statement gave, and then m equal to 2, then go in. Is m less than or equal to n? Yes. 2 is less than or equal to 5. We get to calculate answer equal to the original answer times m. So it's 1 times 2 will give you 2. And then next, m is incremented by 1. From 2 it becomes 3. Back to check whether the condition is still okay. So in this case, m is now 3. 3 is still less than 5. So this is okay. So we go in to calculate. 3 times 2 give you 6. M is incremented by 1 from 3 to 4. And next, back to checking of the condition again, and 4 is still less than 5, so 4 times 6 is 24, and then m is incremented by 1, you get 5. Next is check the condition again, it's still okay because 5 is less than or equal to 5. You multiply 5 with 24, you get 120. Now m is incremented by 1 from 5 to 6. At this moment, the condition fails. You skip the body of the while loop. You reach the statement return answer, which is returning 120. Yeah, so this is the tracing. We have to do this once more for you to see, as this is an important way to understand all this looping and to help yourself to get used to this construct. Wow. So here are the two solutions we have seen. Okay, we have just seen while loop. Here is the definition for while loop. While expression, where expression is a predicate, that if it is true, then the body, this is one or more statements, can continue. Otherwise, you will just skip the body. The next way to do iteration is with the for loop. And the for loop has a special structure that for I in range, starting from where and stopping before this number with a particular increment. Right? So as long as you do not stop, the body will be executed. The difference of this to the while loop is that the I as an index, that it has a value that can be incremented, that you do not have to do it yourself as in the case of the while loop. There's this keyword range that means the following. Range bracket 0, 5, meaning that you start from 0, you end before 5. So this means 0, 1, 2, 3, 4. What about this? Range 5, and this is again the same as range 0, 5. In this definition, the square bracket here means optional. So start is optional. Another square bracket here means step is also optional. But the stop is not optional. So you must have at least range with at least a number. That number, in the case of range 5, is the 5. And starting by default is 0, and the step by default is 1. Range 5 means the same as range 0, 5, that is 0, 1, 2, 3, 4. Next example. Range 1, 5, 2. So we spell out all the start as 1, stop as 5, step as 2. So this means that you start at 1, you end before 5, increment of 2. So you only get 1 and 3. Next, the start is a 5, stop is the 1, step is minus 2. So you start from 5, you end before 1, and you decrement by 2. So you have 5 decrement by 2, 3. 3 decrement by 2 is 1, but you have to stop before 1. So you only have 5, 3. There are two useful keywords that you should know: break and continue. They are used within a loop. At times, you may want to quit completely from the loop before the number I reaches 9 for this case. If I is equal to 3, you want to quit. Alright, so in this case, when you print it out, you only see I takes the value of 0, then 1, then 2, then 3. Once it reaches 3, it breaks. So this loop will not continue all the way until 9. So this is breaking out of a loop. Equivalently, in while, you can also do the same. While I less than 10, you print I. If I equal to 3, it breaks. Otherwise, you increment by 1 and continue. The next keyword we need is continue. Here's an example. At times, you may want to selectively do some statements within a loop. In our example here, print is the statement. That is, you may have certain condition when true, you don't want to continue with the processing. So you basically skip everything within the loop after the keyword continue. In our example here, when I divided by 2 remainders is 0, means that I is actually an even number. We want to skip printing I. So as a result, for I taking the value from 0, 1, 2 until 9, this program only prints out 1, 3, 5, 7, 9. A seemingly equivalent version with while loop is like this. I equal to 0 while I less than 10. If I is an even number, we continue, meaning we skip this print statement and then we go to the next round. But actually this program has a bug and it is not quite equivalent to the one with the for loop. To sum up this slide, the break keyword is to quit the for loop or to quit the while loop completely, whereas the continue is to continue to the next round of the looping. Continue next round of the looping while skipping all the statements after it. Let's look at the factorial example again and try to solve it with the for loop. The iterative thinking is to start with n, multiply by n minus 1, then multiply by n minus 2, all the way until 2. So this is natural to use for loop with decrement of 1 each time. Define factorial n, answer start with 1, and then you use the for loop with index I, ranges from n until before 1 and decrement by 1. So this I in this loop carries the needed number n, n minus 1, n minus 2, all the way until 2. So the multiplications accumulated give you the answer. We can do the tracing here again. I is nothing at the moment and answer is 1 with this first statement. Next we go to the loop. I is initialized with n. For our example of factorial 5, n is 5. So I start with 5 and the answer is 1 times 5 to give you 5. Next you go back. The index I now is to be decremented from 5 to 4 because of this minus 1. So next the answer multiplied by 4. So the answer currently is 5 multiplied by 4 to give you 20. Next again I is to be decremented by 1 and it is now 3. 3 is still larger than 1, so you still continue and the answer is equal to 20 times 3, so you get 60. Next, now the I is 2 after decremented by 1 again, and 2 is larger than 1. Take 60 times 2 to give you 120. I is 2, so 2 is the last number that we can have because we have to stop before 1. So we have completed this loop and now we move on to the next statement and return the answer 120. In comparison to using the while loop solutions, this solution is more succinct because the changing of the number is automatically done with the for loop. As before, we can also do the other iterative thinking by starting from 1, multiplied by 2, multiplied by 3, all the way until n. So here is the answer. Answer equal to 1 for m in range from 2 until n, because this is n plus 1. And it keeps accumulating the answer and return the answer. We now sum up this factorial example. So we have this while loop and we have this for loop. So in either case, the time taken for this while loop to do the calculation or the time taken for this for loop to do the calculation, they are both proportional to the input number n, as you can see from this table. And when n is 5, you have 5 calculations and you have here 4 calculations, so the time is linearly proportional to n. Whereas the space for this program, it uses only the answer, so this is constant space, so there are no defer operations as in the case of a recursion. Same here, it only uses answer and I as variables, so the space requirement is only constant. So in comparison, the time taken for this iterative process is the same as that for the recursion version. But for the space-wide, it is only constant and thus better than the recursion version. What about the other two solutions? While loop, same thing, it's only proportional to n. And this for loop, again, is also proportional to n. So the time is linearly proportional to n, and the space is constant because there are no defer operations, and in the program, it uses only 2 variables. In this program, it also uses only 2 variables. So the time taken is the same as the recursion version, but the space-wise, it is better than the recursion version. Example 2, Fibonacci numbers. F0 is 0, F1 is 1, Fn is equal to the previous 2 numbers added up. So this is 0, 1, 1, because of 1 plus 0, get 1, 2 because of 1 plus 1. This itself is already an iterative process. You start with 0 and 1, and you keep track of the last 2 numbers to get F2, and then you keep track of F1 and F2 to get F3. So here is the while loop. If n is less than 2, you return simply the number. Otherwise, you start with I equal to 2, F, the previous number, is a 1, the previous number is a 0. And then you continue in this while loop. You get the next number from the previous 2 numbers. And then now you have to reassign the current new number and the previous number to become the previous number and the previous number before you move on, and so on. You can trace this yourself to see that indeed this is correct, and you return Fn. In the same way, for loop, you also keep track of F previous one and the previous one. And in the for loop, I is incremented for you. It doesn't appear in here, but it is used to control the number of times this is going to be carried out. So it is carried out until I is equal to n. So each time, Fn is equal to the sum of the previous 2 numbers. And then you have to use this statement like here before to keep track of the last 2 numbers for the next round to calculate Fn. And then you return Fn. Same here, you should trace it yourself, and the variable to keep track of are f minus 1, f minus 2, Fn, as well as I. You can check in these 2 solutions, the time taken is now linearly proportional to n. This is much better than the case of a recursion, which takes exponential time. Let's see our third example. In our previous example, the for loop was a much natural way than the while loop. So what about this one? GCD. GCD of a comma 0 is a. GCD of AB is the same as the GCD of B comma R, where R is the remainder of a divided by B. The iterative thinking is then to keep track of AB and calculate R along the way until B is equal to 0. Then we can stop. In this case, the while loop simply checks that while B is not equal to 0, it continues doing it by B become the next A and the remainder become the next B. You do this until B is equal to 0 and then you return A. So this is the while loop. What about the for? So for for, we must have for I in range something. And what about this range? We can't be sure of the number of times we have to do this, but we know that we will not have to go through this too many rounds, especially we're not going more than B rounds. We can simply use this range to control the number of rounds while I is not being used in the body. In the body, we have A comma B, which is the next A and the next B. It's going to be the B become the next A, and the remainder of A divided by B becomes the next B. Once B becomes 0, we break from the loop and return the answer. So looking at these 2, the while loop seems much more natural here than the for loop. We can now go to the next example. Towers of Hanoi. We are given 3 packs, A, B, C, with 3 disks here as an example. Our goal is to move these 3 disks from A to C while obeying the rule that no bigger disk on top of smaller disk at all time. Previously, we solved this beautifully with few lines of code in a recursive manner. What about iterative thinking? Well, in that few lines of code in the recursion version, we actually rely on the system to keep track of things for us in a stack or a system stack. For here, in the iterative thinking, we would have to do it ourselves with a manual stack then. So how do we do this? Well, this is a case that myself can't think straight to get it done with my own manual stack. I will have to leave it to you. What about this case then? Changing coins. To find the number of ways to change $1 with unlimited 50 cents, 20 cents, 10 cents, 5 cents, and 1 cent. Again, the beautiful recursion relies on the system stack to solve it in a few lines. What about iterative thinking then? Same here, I have to leave it to you as I can't think of it as a natural iterative thinking. Why is that so? You notice that this example and the previous one on Towers of Hanoi both are actually exponential recursion. In exponential recursion, a manual approach to keeping a stack is quite a hairy task, though it's not impossible to do. On the other hand, for this changing coins problem, there are actually good ideas to solve this iteratively in an efficient manner. We will see this in a later lecture. We now sum up recursion versus iteration. In a recursive process, the recursion occurs with defer or pending operations, and the computer system handles it for our convenience, using system stack or more formally activation record. And so this defer pending operation costs extra space needed to run the program. On the other hand, in iterative process, there are no defer operations. Everything you need are simply while or for loops available in the language. So recursive solution, conceptually easy to obtain, but it can be expensive because the extra space to keep track of the pending operations. Also, you see that you may cost exponential time too. While in the iterative process, things could be handled more efficiently, but it is hard for us to handle manually the stack, especially in the case of exponential recursion. And for this course, you don't hesitate to write recursive processes. We will leave the optimization to the interpreter. We will concentrate on problem solving either with recursions or with iterations. Whatever needed from you in assessments will be spelled out explicitly.